Dear students, in this lecture we will study ratio tests for convergence and divergence of series of real numbers in absolute form. Let us first see ratio test for convergence and of series of real numbers in absolute form. The series An is a series of non-zero real numbers. We define the number A as limit inferior of the sequence mod an plus 1 upon mod an and B as limit superior of the series mod of the sequence mod an plus 1 upon mod an. So A and here I should write capital A. This is how we define. Then the statement states that if limit superior is less than 1, so then series an converges absolutely, that is mod an is convergent. If small a, that is limit inferior, is greater than 1, then series an diverges. And if 1 lies between a and a, that is limit inferior and limit superior, then test cannot be applied, it fails. Let me recall what is A. A is limit inferior of the sequence mod an plus 1 upon mod an, and capital A is equal to limit superior of mod an plus 1 upon mod an. Let us recall this. Now first part of the proof. Choose a real number b such that a is less than b is less than 1, so that b will be of the form a plus epsilon for some epsilon greater than 0. Now consider the given fact. B is less than 1 and it is greater than a. Okay. So by known results on limit superior and inferior, there is n belongs to I such that if n is greater equal to n, then mod an plus 1 upon an is less equal to b, because b is less than 1 and it is greater than a. Okay. Sorry. So we have a is less than b and b is less than 1. Now use the basic results or basic inequalities. It is greater than limit superior. So every term of the sequence will be less equal to the number superior, and b is indeed greater than superior. So every term of this sequence, which sequence I'm referring to? I'm referring to the sequence mod an plus 1 upon mod an upon mod an. So all terms of this sequence will be less equal to b. Multiply these inequalities, and if you multiply all these inequalities, we could get that mod an plus k upon mod an is less equal to b into b into b k times, that equals to b raised to k. So thus we proved that mod an plus k is less equal to mod an into b raised to k. It means that the series mod an is dominated by series mod an into b raised to k, where n is positive integer n, such that this condition gets satisfied. Okay, so it means that the series, which series I'm referring to, it means that the series mod an is dominated by series mod an into bk. Mod an is constant, so I'll take it outside. So it means that this series mod an is dominated by mod an times the series p raised to k. But as b is less than 1, the series, it is a geometric series, k is equal to 0 to infinity, geometric series b raised to k, it is convergent. So for this reason, I have in fact this result. So by this result, if the series mod an into this series is convergent, this series is convergent. Now apply comparison test in absolute form. If bigger series, if bigger series is convergent, this is bigger series is convergent, then smaller series, that is mod an, is also convergent. So smaller series mod an is convergent by comparison test, because bigger series is convergent, and hence the smaller series mod an is convergent. Recall that our hypothesis was a is less than 1 in this case. Now in second case, the second part of the proof, our hypothesis is that a is greater than 1. So to prove this, let us consider the given fact. What is a? A is nothing but limit inferior of the sequence mod an plus 1 upon an. We have seen several results on limit inferior and superior. So by using this result, we can write if n is greater or equal to n, then mod an plus 1 upon an is greater than 1, because a is greater than 1. So by one of the results which we have seen, we could write this. This implies that mod an plus 1 upon an, mod an plus 2 upon mod an plus 1, mod an plus 3 upon mod an plus 2, and so all these are greater than 1. Hence we have the inequality that it is greater, every term of the sequence mod an goes on increasing, that is the sequence mod n is equal to 1 to infinity is non it is non decreasing sequence. It is non decreasing sequence. Further, it is series of non-zero terms, so it is greater than 0. So it means that definitely that limit of an is non-zero, and from the necessary condition for the series of convergence of real numbers, we know that this series an cannot converge, it diverges. And if the series diverges, then we can definitely say mod an, the series mod an also diverges. So let us see the final step in the proof that series an is divergent. Now the final part of the proof, a is equal to 1. So just to support the final statement, we just need to give examples. If we consider these two series, series 1 by n square and 1 by n, for this series a is equal to 1, but the first series is p series with value of p greater than 1, so it is convergent. But the second series 1 upon n, it is harmonic series, we have proved that it is divergent. So thus test cannot be applied when a is equal to 1, or when we have the statement that 1 lies between a and a. So in that case test cannot be applied. One example is sufficient to support the statement. Basically you remember that root test says that if limit of the ratio, so by using root test we can definitely say if limit of this mod an plus 1 upon mod an exists, in that case limit inferior and limit superior will be equal, and if this limit is less than 1, then series is convergent. And which series? Series an. And if it is greater than, then series is divergent. So this is how we practically apply root test. If limit of absolute value of ratios is less than 1, then series is convergent, and if it is greater than 1, then series is divergent. Thank you.